Okay, so this is about transformations of the complex plane. This is part 3. In part 2 we looked at basically one long example where we showed that a transformation, a Mobius transformation, could map a line to a circle and sort of showed that was true. Here's another question along the same sort of idea. So we've got a new transformation here, w is equal to z plus 2 over z plus I. It's another Mobius transformation, linear term top, linear term bottom, contains some complex numbers like I. That's okay, it's allowed. Show that the imaginary line in the z-plane, so that's this line over here, right, is mapped to a line L. A line this time rather than a circle, could go to either one, in the w-plane. Find the equation of L. So we've got to find the equation of what this line ends up being. It could be a line like this or a line like this, or I don't know. We'll find out. We've got to use this information. We've got to explain what this means. So what does it mean for something to be an imaginary line? Well, I suppose that would mean that your y value can be anything you like, but your x value must be 0. There's no real part, it's only an imaginary part. So the bit of information we have now is that x is equal to 0. Again, we've got to use that and just this information here, just this transformation, to work out what the new equation L is. So to do that, we need to use the fact that x is equal to 0. And one of the easiest ways of doing that is to rearrange this for z. So let's take w is equal to z plus 2 over z plus I, all times by z plus I. We get wz plus wi is equal to z plus 2. Oh, look, there's two z terms, so we'll have to move the z terms to one side and factorise the z out. We can move this to the other side. There we go. And now we need to factorise the z out. So the z comes out of the factor, and we're left with w minus 1. On this side here, we've got 2 minus wi. And then we'll divide by w minus 1 to give ourselves that. Which is now in terms of z. So same stat as before, different equation, different rearrangement, but the same idea that we're rearranging for z. We're now going to do the same as last time, which is plug in x plus iy and u plus iv. We're trying to get it so this right hand side is written as a real imaginary part, and so we can use what we know about x. Okay. So to do that, we'll start by just grouping the real and imaginary parts together up here. So we'll have a 2, we're going to have a minus ui, we're going to have I times I minus 1 times that's going to be a plus v. This is very familiar, isn't it? And then over here we've got u minus 1 this time and plus iv. And I always like to get my real and imaginary parts together before I start doing any kind of expanding out. So I'm just going to rewrite that top so that it's 2 plus v and then minus ui. I do that because I really prefer it when my real and imaginary parts are together. It makes it easier for me to see if I've gone wrong anywhere. I'm now going to times by the complex conjugate of the bottom to do that, to make the bottom real. And so I've got times the top by the same complex conjugate. Okay, and so we know the bottom's going to be very straightforward. It's going to be just the real part squared and the imaginary coefficient there squared, because it's different to two squares, and this time because you've got an I times an I, you get a minus 1, which cancels that minus sign to make a plus, and the in-between terms cancel out. At the top, we'll do the first two, because that's going to give us a real number. We're going to do the last two, because that's going to give us a real number 2. So we've got I times I, which is minus, that's the first minus sign. We've got another minus sign there, and a third minus sign, so that's 3 minus signs in it being minus, and then the u times the v. That's our real part. We now know we're going to do imaginary parts, so we do these two middle terms. Minus u times u minus 1, and the I is already there, and the outer two terms, so I've got the I already there, so I've got minus v times this bit here. Minus v, can I squeeze this in? Yeah, just about. Actually, we may ask ourselves later whether we need to work out that imaginary term. We'll see what I mean. So now I've got it as written as a real term and an imaginary term. So I can say the real part over the bottom, because everything's divided by that. X is equal to that, and the imaginary part things like that. Again, we can use what we know about x and y. So we now know that x is equal to 0. We don't know anything about y. Y could be any number we like, but we know that x has to be 0. So I can put this is equal to 0 over here. Cover up the x. We can see that we've now actually got a Cartesian equation. As before, we times by the bottom, times it by 0 makes the equation quite nice and easy. Because 0 times anything is still 0. Expand this out. So we've got 2u plus vu minus 2 minus v, I think. Just double check that. 2 times u, v times u, 2 times minus 1, v times c. I do this in the order you like because it's not the same as doing real imagining, isn't it? Okay, so this minus uv and this vu, these cancel out, which is good. And now we're left with 2u minus 2 minus v equals 0. In fact, if I rearrange this, bring this v to the other side, I'm doing that because v is like y. I've got v is equal to 2u minus 2. Can you see that's the same as the equation of y is equal to mx plus c? In case you're thinking I'm going crazy, I've drawn this as being a u and this being a v because I'm doing about the uv plane, not the xy plane, right? Oh, can you see that at the bottom there? Yeah. Okay, so this means I've got a line that goes through minus 2 on the v-axis. It has a gradient of 2, and we can work out where it goes through the u-axis by thinking what value of u do you put in there to get 0 out? Well, if I put a 1 in, 1 times 2 minus 2 is 0, so it must go through here at 1. Basically, I'm solving when v is equal to 0, aren't I? And when u is equal to 0. When u is 0, I get minus 2. When v is 0, I get 1. And there is your line. This is my line L. This is the equation for L as required. Just look what we've done though. Look how similar it is to the last one. This is not always the case, right? The information you're given here dictates the way of doing it. And because I got told about x, I used this format. They could have told me something else here. Maybe they told me, show that the line x equals y goes to some circle or goes to some line or whatever they say. In this case, if you're told this kind of information, you would, at this stage here, rather than setting x equals 0 and y, forgetting about it, you'd be saying that this term and this term are equal and writing that is equal to that. So the key to these questions is to use the information you're given. Is it the fact that you know that x is 0? Is it the fact that you know that y is 0? Is it the fact that you know that x and y are equal? Use the information about x and y you know, and at this stage here, you get there the same way each time, but at this stage here, you do different things based upon what information you're told, okay? So think about what information you're given. Questions are not easy, but they start the same way. Start by rearranging for z, and then computing what x and y are, and then here it may change based on what information you've got there. Okay, there is a different type of transformation, one where you get told about the modulus of z, and that is what I'll cover in part 4. So look forward to that. Good luck. See you soon.